This is homework 0 of Introduction to Logic Design. We're going to be going through about 20 problems related to very simple topics, and this will help with labs and other future homeworks. So for our first question, we are asked, using the color codes, determine the value of each of the resistors. So for question 1, we're asked, using the color codes to determine the value of each of the resistors. When we're adding for resistors, when we have 3 lines of resistance, we are going to kind of use this formula where we have our first line, we have our second line, we have our third line, and then lastly, we will have some fourth line. And this first line is going to be our A. The second line is going to be our B. Our third line is going to be the C. And this is just going to be our percentage. So when we write this out, we are going to have an A. We are then going to have B. And then this is being multiplied by 10 to the C. And then after this, we are just going to have some percentage. And this is the plus minus tolerance. In part A of 1, we have red, orange, red. Red, orange, red is going to be 2, 3, 2. So we can write this out as 23 with a 10 squared, or 2,300 ohms of resistance. So that is the answer for part A. For part B, we have brown, black, orange. Brown is 1, black is 0, orange is 3. So if we write this out, we're going to have 10 times 10 cubed. And this is going to give us 10,000 ohms, or we can write this as 10 kilo ohms. And that's the answer to part B. Now we're going to look at part C. In part C, we have orange, orange, orange. This is going to be 3, 3, 3. So when we write this out, we're going to have a 33 times 10 to the 3, which is cubed. We're going to have 33 ohms. We're going to have 33,000 ohms, or 33 kilo ohms. That's the answer for part C. Next, we have part D, where we have brown, black, green. Brown is 1, black is 0, and green is 5. So when we write this out, we are going to have 10 times 10 to the 5th. And this is going to give us 1 million ohms of resistance, or we can write this as 1 micro ohm. And that's going to be the answer for part D. In part 2, we have a resistor with color bands red, 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 gold, and we have to find the value for it. So we know red is a 2, so we're going to have 2, 2, 2. But what is gold? Well, I mentioned the percentage sign earlier here, and there's different percentages. If we have no band, so if there's no band at all, we have a 20% tolerance. If we have a silver band, we have 10% tolerance. If we have a gold band, we have 5% tolerance. So this is going to be 5% tolerance here. Now when we rewrite this, we're going to have 22 times 10 squared, and then our 5%. So when we write this out, we're going to have 2200, or 22,000 with a 5%. This can also be written as 2.2 kilo ohms of resistance with our 5%. So it's not 22K, it's not 22, and this R is just for resistance. It's not 220, so it has to be B. Our answer is going to be 2K2 with a 5%. In part 4, we have resistors in ascending order. So order going from least to greatest. And when we're looking at these, we're going to have R for just regular resistance. Next, we have a kilo of resistance. Then we're going to have a million of resistance. So when we look at this, we're going to look at A first. Our R looks good. Our K looks good. However, this 270 is greater than this 2K2. So this messes up our order, and that's not going to be our answer. Now we're going to look at this. This looks good. This looks good. This does not look good though, because we have a resistance, or regular resistance, after our Ks. So that messes up this order. In part D, we have 3R3, so that's good. We have 4R7, that's good. We have a 22R, that's good. And then this is good as well. So part C would be our answer. Now in part D, we have 100R, so that's good. We have our K, that's good. We have a milli, and then we have this 3K3. This messes it up, so we know that would not be your answer. That's how you'd solve this problem. If in part 4 we have if 2 resistors are placed in series, what is the final resistance? Is it higher, lower, the same, or can it not be determined? Well, it can always be determined, so it's either going to be higher, lower, or the same. So when we draw this out, we have a resistor like this, and then we have a resistor like this. They're both in series. This can also be drawn like this. They're both the same. And we know that resistors in series are just going to add together. And if they add together, it's going to give us a larger number. So that means that the resistance as added together is going to be higher. For part 5, we are told that a red, red, red gold resistor is in series with an orange, orange, orange gold resistor. And we need to see what that produces. So if it's red, 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 looking at the table, we know that it's going to be 2. And then for the orange, it's going to be 3. We are going to have a 2 times 10 squared. And then we are going to have our gold resistor, which is 5%, plus our orange, so 3 times 10 cubed per orange. And then we're going to have 5% resistance. Now, if we write these out, we are going to have 22 or 2,200, and then we are going to have 33,000 with 5% each. So if we add these both together, we are going to get 35200 with 5% tolerance, or we are going to have 35.2 K, and this is 5%. So these will be our two answers. It's obviously not going to be A. We don't have a 5. We don't have 55. It's not none of the above either, because our answer is B, is 35,200 ohms, and that's what we wrote right here. Next, we're asked what a 10K resistor in parallel with another 10K resistor produces. Resistors in parallel follow this formula. We have 1 over our resistor plus 1 over our next resistor, and this would continue for as many resistors as we have. All of this is in parentheses raised to the negative first power. So if we rewrite this, we are going to have 1 over 10 plus 1 over 10, and this is being raised to the negative first power. I forgot about the K's right here. This is given to us in kilo ohms, so we have to write this in kilo ohms. And this is going to give us 5 kilo ohms. A trick for this is that if we have two resistors and they are both of the same resistance, when we have them in parallel, so 10K is in parallel with our 10K, if we come out the other side, it's just going to be half the resistance. That's going to give us the 5K. And so our answer is going to be B for number 6. For part 7, we were asked to obtain a higher value of resistance. Resistors are connected in what? We have reverse, forward, parallel, and series. Well, resistors don't have polarity, so there is no reverse and there is no forward. And previously, if we look back up here, we can see that resistors in series, so for like number 5 or number 4, where the answer for number 4 was higher, we can see that the answer is clear to be series. If it's in parallel, it's going to be less, and if we want a higher value of resistance, it's going to be more in series. So for 7, we're going to have D as our answer. Part 8, we're asked for the closest value for our combination. We can do the trick since these are both the same resistance. We're going to have 4K 7 divided by 2. And this is going to give us approximately 2K3. So that means that B is going to be our answer. For 9, we're asked what does the acronym LED mean? LED means light emitting diode. So it's not light emitting display, not low energy display, and it's not light emitting detector. It is light emitting diode. Next, we're asked what is the appropriate characteristic voltage that develops across a red LED. And for this one, we can draw a little diagram. We are going to have our voltage, the power source. It's going to be 5 volts. And then we are going to have our small circuit like this. We are going to have our red LED be connected like this. And then we are going to have some resistance connected like this. So the red LED is 2 volts. That's approximately 1.7 volts, and that's what that would be. And then our resistance would be a 3 voltage resistor. Part 11, we're asked to identify the correctly connected LED. We're going to look at A first. There's no resistor here, so this LED would burn out. It's not connected correctly. Same thing for D, would not work. Now we look at B and we look at C. Now for B and C, they're very similar, except that the direction of our actual LED is incorrect for C. It needs to be facing away, or the bigger part, like an arrow, has to be facing away from our voltage source, because if the current flows through this way, it's going in the same direction as the arrow. The arrow goes like this. we can see that the arrows are conflicting here. That means it cannot be C, and it has to be B. For the resistor itself, the actual resistor can go after LED or it can go before the LED. We just have to make sure that the direction of the LED in our drawing is correct. So for number 11, we are going to have B as our correct value. In part 12, we're asked the current requirement of an LED, and most common LEDs require an operating voltage of between approximately 1.2 to 3.6 volts. We found that in part 10. Our forward current rating would be about 10 to 30 milliamps. Well, if we go off that knowledge, it cannot be A, 10 to 30 milliamps. We'll write this right here. And it cannot be B, because it's just 25. It cannot be D. The only thing with a range is our C, between 3 and 35 milliamps. Next, we're asked to identify the correct statement, and it is about our LED right here. The longer side is longer. It's going to be the anode, and our shorter side is the cathode. Now, the anode being bigger, greater, is positive. Our cathode being smaller is going to be the negative. Part A says the cathode lead is longer. That's false. Part B says the cathode lead is shorter, and it goes to the negative rail. So that means our answer has to be part B. If we look at the other ones, it says for part C, the cathode lead is shorter. That's correct, but it does not go into the positive rail, so that's incorrect. And then it says the cathode lead is longer. This is incorrect. So for sure, our correct answer is B. In part 14, we are asked the direction of conduction for a diode. When we look at this, it cannot be part C because it's not multi-directional like this. And it's not going to be part B because it has to be going in the same direction. For that reason, going in the same direction, we are going to have part A. So for 14, part A is our answer. 15, we have 1 milliamp is equivalent to, and this is just conversion. 1 milli is equal to 10 negative cubed. So we're going to have 1 times 10 to the negative cubed. We can rewrite this as 1.0. So we move it once, twice, and then a third time. We could fill these in with zeros and put our decimal here. And that's going to give us a 0.001 amps. 16, we're going to do the same. We have 1200 times a 10 to the negative cubed because it's a milli. So we will have our 1200.0. We're moving this over 1, 2, 3. So that's going to leave us with a 1.2 volts. That means our answer for 16 has to be B. For 17, we're asked if a 10K resistor, so we'll draw our resistor, is placed across a 10 volt power supply. We'll draw our power supply in black over it and be plus minus, and this is 10 volts. We need to find the current. Well, using Ohm's law, current is equal to voltage over resistance. Current is equal to our 10 volts divided by our 10K resistor in this case. Remember that 1K is equal to 10 cubed. And if we do this, we are going to get that our I is equal to 0.001, and this is measured in amps. Now, we don't have 0.001 amps. We do have a lot of milli, though, so we're going to convert this. We are going to multiply this by 1 milli, and we have to divide it by 10 to the negative cube, because that's the equivalent. And then we're going to have 1, 2, 3 moved over. I is equal to 1.0 milliamps. So when we look at this, we have 1.0 or 1, and that is our B. 18, we are asked a DC voltage. What is it? And a DC voltage is just a constant voltage. It's constant like this. It does not rise and fall. It's not sinusoidal, and it is not in an audio waveform. So it's constant and it's C. Part 19, we have for the XOR gate, what is the output when both inputs are high? This is also known as the exclusive OR, and if we look at the notes linked below the like button for the discrete structures, which is a different course, it actually has information on this in page 16 at the bottom, exclusive OR. This is basically, we have to let our inputs be two logical statements. And these two logical statements is for an exclusive OR again. And this only works, this is only exclusively works if our logical statements differ. And so true is equal to high. That's basically what these mean. These are equivalent. So it is high if our logical statements differ, or the output, which is what we're looking at, is high only if our two logical statements differ. But if they're the same, then it is going to be low. So in our gate, this value is high or true. This value is high or true. So that means the output, it says if the logical statements differ, it is high. Well, since they're the same, it's going to be low, which is the opposite of high. And it has to be low, again, because both the inputs are the same. It's only going to be high for the output if our statements differ. Also in the notes is the logical term conjunction, which is our AND gate. And our AND gate is only true if both our inputs are true, or we can say that they are high. So it's only high, the output is only high if both of our inputs are high. So when we look at this, we're given that our both inputs are high. So we have high here and high here. Again, since they're the same, that means our output is going to be high, and that's just because of the logic. And that is how you would go about finishing this worksheet.